Hello, everybody. Welcome to Module 8, Secondary Treatment with Fixed Media. For the lecture, we're going to cover the material in the Ragsdale Wastewater Operator Review Manual, Chapter 7, and the same Chapter 7 in the New Mexico Environment Department Study Guide for Wastewater Operators. So, fixed media is a little different than what we've been talking about with respect to clarifiers. Uh, Next chapter or next module, we'll talk about activated sludge. And we'll see in the activated sludge chapter that in our secondary clarifier, the microbes are floating around in the clarifier. So they're free floating, if you will, and they're metabolizing the organic waste in the waste stream. The fixed media reactors are a little different. In fixed media reactors, we have a biological film or a slime, if you will, that covers the filter media. We'll find that the rock and the other media that we have in trickling filters, the biological mass is attached to those, and we pour wastewater over that media and allow that wastewater and the organics to come into contact with this uh, film or slime, if you will, and it's on a fixed media. So the film is attached to rock or other filter media in a trickling filter, and we trickle the wastewater and the organic load in that wastewater over that media that has the slime layer attached to it, and that's how those microbes metabolize or chomp away at that waste. We have a second type of device called a rotating biological contactor. And in those rotating biological contractors, we have these large drums with surfaces, kind of labyrinth or maze like surfaces, whereby our biological film is attached to those surfaces. And we rotate these drums so that the film gets dipped into the wastewater with the organic load very slowly. And we just have these rotating drums or barrels, if you will. And that's how we facilitate the contact between the microbes and the organic waste load. Okay. So the fixed media principle is the microorganisms, or the bugs as we call them in wastewater treatment, they're growing attached to a stationary surface instead of being suspended in water. So a bit of a different perspective. And what happens is we trickle or pour or shower the wastewater with its organic load over the media, so that dissolved organic food is being fed to that film, which is where all the microbes are hanging out. Okay, so a little different perspective. And the oxygen, we're providing oxygen because air is circulating between those filter media or surfaces, or mechanically, in the case of rotating biological contactors, we're actually dipping those in and out of a water surface or wastewater surface and exposing them to air. So we're also aerating that waste, if you will, and allowing the biological film to get oxygen to get that aerobic condition, so that we're allowing them to metabolize that waste. Okay, so different perspective. And we are looking at trickling filters. We have what are called high rate trickling filters, standard rate trickling filters, uh, bioroughing filters, trickling filters. We also have nutrient or nitrifying trickling filters. And then we have a separate classification of material, or I'm sorry, of systems, rotating biological contactors, or RBCs. You know, we love acronyms in wastewater and engineering. So RBCs are rotating biological contactors. Um, this is a very important note right here. Pre-treatment. Primary treatment or clarification, allowing the heavier sludge particles to settle out, it must always happen before we introduce wastewater to the fixed media. And that's going to prevent the heavy sludge and grip particles from settling into the trickling filter or clogging up our biological contactors. Very important concept here. It's a mandate. if we don't have a pre-treatment or primary treatment prior to this biological process of fixed media, whether it be a trickling filter or an RBC, we're going to clog up our whole system and we're going to accomplish nothing but creating a mess for ourselves. So that must always happen. Okay, that's a really good test question, just so you know. True or false? Do we always have to have primary treatment prior to fixed media secondary treatment? The answer is yes, must always take place. Okay, so let's start off with trickling filters. Um, and this is covered pretty well in both the Ragsdale Manual and the New Mexico Environment Department Study Guide. Matter of fact, both chapters are close to identical. The one big difference between them is the Environment Department Study Guide gives you a list of components for both the trickling filter and the rotating biological contactors. And for level 1 and 2 folks, I would take a look at the components because you're expected to help maintain those and conduct maintenance checks on those. Level 3 and level 4 folks, you definitely want to know the biological processes taking place here, as well as all of the components and what have you. So there is some good material in the Environment Department Study Guide, but as always, I strongly recommend you start off by reading the Ragsdale Manual because his writing style just pops out at you, and he explains the material extremely well. So, again, what I would recommend, read the Ragsdale Manual, watch the lecture, and then read the Environment Department Study Guide. And you'll also find some YouTube videos that I posted. There is one in there from a gentleman, the very last video I posted, who calls himself the wastewater enthusiast on YouTube. His whole channel revolves around giving you practical looks at what's on the certification exams. So what he does is he actually takes a video camera out to his wastewater plant. Pardon me. He lets you see the physical process, then he gives you a whiteboard lecture and tells you what he thinks is going to be on the exam. And he's very effective. So I do recommend his videos. I posted one for you on this, and it's a really great video. Okay. So getting back to the trickling filters, components, and biology. Okay, first thing you want to see, and we'll see the schematic in just a moment, you got a distributor assembly, and that's just an arm that rotates around a circular filter, okay? And it's driven by this hydraulic reaction force and basically pressurized wastewater coming in, and it's going to trickle or shower whatever effluent is coming out of the primary clarifier over that filter bed. And as you can imagine, it's not going to be a high pressure spray, because if it was, that would wash off the zoological film or zoogilo, uh, zoogilo. And I'm horrible. Matter of fact, I probably have an undiagnosed speech impediment, but the slime layer. If we had a high pressure stream of primary clarifier effluent entering the trickling filter and spraying out over our filter bed, we would wash away that slime layer and we wouldn't do ourselves any good. So that's why the trickling uh, name on the trickling filter comes about, because that's what you're looking at for a flow rate. It's going to trickle out rather than shower or spray out at a high pressure. Okay, so that's the first thing you have is just a rotating arm. The water or wastewater coming out of the primary clarifier is going to move that along and trickle that over the filter bed. Okay, just a rotating arm over the filter bed. Then you've got the media, the filter media, and that's in a bed. And the idea is you get a high surface area to volume. So the rock that we use, or if we use any other filter media, it's not sand, it's rock that has a high surface area to allow the maximum amount of film or optimum amount of film with microbes to grow there relative to the volume. So we want to make sure we have enough surface area for this film to house those microbes and to have the wastewater trickle out over it so that those microbes are chomping away at the organic load. We also have an under drain system at the bottom of the tank, the filter bed, and that's going to collect the filter effluent, and it's also going to allow for ventilation, for air to circulate through that filter bed, thereby giving us aerobic conditions or an oxygen-rich environment for these microbes to metabolize the organic waste. And then we've got the Zoogill slime film, and I call it the slime, uh, or snot layer, if you will. And that's an active biological layer. It's composed of microbes, bacteria, protozoa, and the dissolved and suspended organic matter that's being trickled over that, the microbes, bacteria, and the protozoa, that they're going to chomp away or metabolize that as we pour it through. And then you have natural sloughing, is what it's called. And that process is when that biological mass or that slime layer starts growing and gets heavier, it'll break off the media and it'll settle in a secondary clarifier as sludge. So it's kind of a self-regulating film. We're feeding the film, we're letting it grow on the rock or the filter media, and it's going to multiply because that's what the microbes do. As they get more food, more oxygen, they'll start multiplying, and they'll start breaking apart. There's more of a biomass, and as that slime layer becomes thicker and heavier, the natural sloughing is just it breaking away and settling out. So it's kind of self-regulating. It's pretty cool when you think about it. And here is a just a schematic. This is in your book, and so we have the rotating arm. So it's basically, here it is right here, and it's spraying, or trickling is a better term. And as it trickles, that water motion, it's just going to make that arm rotate. So here's your distribution arm that we talked about. Here's the filter media, okay? And we have a base right here at the bottom that makes sure that we can support the filter media. And what's happening is the influence coming in, and it's coming out through the distributor arm and making that distributor arm move, and it's just trickling out, moving around, and the wastewater trickles through the filter media, and that's where most of the action, if not all the action, is taking place. And then you've got some ventilation ports on the side of that tank that are allowing oxygen to come in. And it's a retaining wall here. It's basically a concrete type basin. Okay. And then you've got the under drain filter, and you've got an outlet valve. So you can open up the outlet valve, and as the treated effluent or treated wastewater comes out, it'll gather and it'll get sent out to the next process via the outlet pipe. Okay, it's a sloped floor, which means that it's going to slope the drainage to the outlet. Okay, we're not going to need a pump, we're not going to need anything like that. So it's a fairly simple type uh, system here, but it is very effective. Okay. And this is something you want to take a look at here. This is table 7.1 in the Environment Department study guide. I have no doubt that you are going to see level 1 and level 2 in particular. You're going to see the part, and then they're going to ask you what the purpose is. Okay. With the, you'll also see it on level 3. Level 4, maybe not so much, but you will see this. And it's a good idea to take a look at that and take a look at the previous diagram and match them up. And I think you'll get quite a bit out of that, but I'll leave that to you in your studies. Okay. But you will see a couple of test questions on this. Okay. And for level 3, level 4, level 3 and 4, you may see, you know, a bit of troubleshooting, like what do you do for an RBC in the event of a power failure? What are some of the nuisances you can see in a trickling filter? And we'll cover that. But that's the kind of stuff you'll see on a level 3 or 4. Okay. So there's three principles or three parts to a trickling filter. There's the media and restraint and retaining structure. So that concrete tank and the rock or whatever type of media you use, that's the first component or first part of it. The under drain system is the basically just the bottom of the tank where you saw those ventilation ports that allow for oxygen to come in, and then you allow drainage to settle out there and then slope down towards the outlet. Then the distribution system, that distribution arm that allows or serves to bring in the influent to the trickling filter, which is effluent, what's leaving the primary clarifier. So these are three items you should be able to recite just off the top of your head when somebody asks you about a trickling filter: the distributor arm, the under drain system, and then the filter media and the retaining structure. Three basic parts. Trickling filters have been around quite a bit of time, and they're still very effective when you think about things. So they've stood the test of time. Uh, and like I said, I think they're simple but very interesting systems. Okay. So the media, the first part of the basic components or part of the trickling filter system. Okay, so again, the media it serves to provide a large surface area so that biological slime is going to grow and develop. And again, I have a problem pronouncing it. The zoogeal film. It provides those living organisms that are going to chomp away or metabolize and break down that organic material of the wastewater coming into the trickling filter. So the media, it can be rock, slag, coal, bricks, redwood blocks. You can even see plastic, some molded type plastic media, which are like spheres with rings around them. And again, the whole idea is to maximize surface area. And if it's a sound durable material that allows a large surface area, you could probably use it. Typically, though, for different flow rates, there's one I think that you really want to use rock only, but you know, take a look at that. Okay, so the idea is we want to be able to stack this filter media, whatever we're using, to make sure that we have enough voids or empty spaces for the air to ventilate the filter and keep an aerobic environment, an oxygen-rich environment. Okay, for rock, the size is going to be about 2 to 4 inches in diameter, and we want it to be uniform. We don't want a bunch of different sized rock. We want it to be fairly uniform so that we have enough spacing for ventilation and to create that oxygen-rich environment. Okay. The media depth, it's going to be 3 to 8 feet thick for rock media, trickling filters. And if you're going to use other stuff like the plastic, the coal, the bricks, what have you, probably going to be twice that. It's going to be 15 to 30 feet for synthetic media. So this is why you'll see rock is still a preferred media, because you're dealing with a lot less space to get the same type of effect. Okay. The underdrain system, the second part of the three-part or three components of our trickling filter system. So we've got a sloping bottom, and the whole idea is as the filtrate comes through, that wastewater comes through the filter, it's treated, moving slowly, hits the bottom floor of that tank, it's going to slope. And we don't have anything mechanical moving that water to the outlet other than the slope. It's just going to slope and drain to the outlet. So it's got a center channel, and it's going to collect that filter effluent and take it out. The underdrain system, it can be redwood stringers or prefabricated blocks made out of concrete, vitrified clay. I've seen pumice in some cases or other suitable material. But the idea is it's going to allow that filtrate to come down, collect, and get moved or flow towards the outlet. The distribution system, that arm that we saw in the schematic, it's just a rotary type, which means it's going to go in a circular fashion, and it's got a couple of horizontal pipes. It's a few inches above the media filter, and it's supported by a central column in the center of the filter, and it's gravity fed from the column through the horizontal pipes, and it's just trickled over the media through orifices or slots on one side of the pipe. Okay, and by trickling that's also going to allow the movement of that pipe. Okay, so that's the idea here, is that rotating water sprinkler reaction. It's gonna serve to also slowly move that pipe in a circular fashion. That's why we only have holes or slots on one side of the pipe, because if we had it on both sides, it'd probably go a little too quick and strip that film. But this is what allows us to have that trickle and allows the distributor arm to move around. So there's a mechanical type seal at the center of each of the pipes, and that's going to allow or prevent leakage, and it's going to allow the bearings to be protected, because we do have bearings in that column that are allowing the distributor arm to be supported as it moves around. Okay. And attached to the center column, you got stray rods for seasonal adjustment of those arms to maintain that even distribution over the media. And you do have an arm dump gate at the end of each arm. It's just basically like a flapper valve. You can pop it open and it'll dump at the end of each of the pipes of that distributor arm. So think of a distributor arm as a cylindrical pipe, if you will, slots or holes on one side of it, and then on the end of each side of that cylindrical pipe, you have pop outs that'll allow for flushing. So you do want to know how we classify the fixed media filters, the trickling filters. Okay, so we've got standard rate filters, and it's shallow rock media. And this is a good test question. What type of media would you use for a standard rate filter, trickling filter? You're going to want to use rock. Okay, and that's going to give you a fairly high efficient BOD removal. You're going to get 80 to 85% of your organic waste, your BOD, out of a standard rate filter. But again, it's shallow, and you're going to use rock. You're not going to use the plastic or anything else for a standard rate. Now, for a high rate filter, yeah, we can use tall, those plastic spheres with, circles, discs around it I told you about, anything that'll allow a high surface area and will allow for high volume loading. And you're also going to recirculate that in a high rate filter. Okay, this is why you're also going to have a deeper filter bed, because we're, with the standard rate, we're keeping it at a fairly decent trickle, so that we don't strip that slime layer off, that biological film off. But on a higher rate filter, we're going to move it a little quicker, but it's also a lot deeper, so that we still have that film throughout our filter media. Okay. Now, roughing filters, they're a classification of filter all unto themselves. Those are preventing shock loads for downstream processes. Think of these as a shock absorber or a buffer. The idea is those roughing filters, they're going to do what they can do to make sure that we take a good chunk of the BOD out of the waste stream or the wastewater at this point, so that we don't shock anything downstream and overload it with a bunch of organics. Okay, that's a roughing filter. Okay, and the differences between a standard rate and a high rate trickling filter. Okay, so a standard media, again, it's going to be 6 to 8 feet of rock. That's what we're going to use for our filter media, rock, for a standard flow rate trickling filter. For a high rate, we're going to go 20 to 25 feet deep. It's going to be fairly deep, and we're likely going to use plastic media. You can use the redwood slats and put them in a tall configuration, but mainly you're going to see like plastic, and it's going to be much deeper. Okay, so for standard rates, it is going to treat 15 to 20 pounds of BOD. Should have put BOD in there, but I didn't. Pounds of BOD per day per 1,000 cubic feet. I think the last lecture I told you we use some funky units in wastewater and engineering. This is one of them. So we're looking at pounds of BOD per day treated per 1,000 cubic feet of wastewater. Okay, so it's 15 to 20 pounds of BOD per day per 1,000 cubic feet of wastewater. High rate filters, that's about 3 times that. 40 to 60 pounds of BOD are treated per day per 1,000 cubic feet of wastewater. The hydraulic loading, the standard rate filter, trickling filter, is going to treat 1 to 4 million gallons per day per acre surface. Okay, we're looking at the surface of the filter, and it might be a small amount that are fairly big, but they're not an acre large. But that's what we treat, 1 to 4 million gallons per day per acre of filter, surface area filter. And the high rate, you're looking at treating hydraulic flow of 10 to 40 million gallons per day per acre of filter surface. And again, I'm going to stress this again, the bioroughing filters, those are high rate units. Okay, so they're high rate units, and we place them upstream of an activated sludge process. Like if we had a problem with a large amount of BOD coming into our wastewater plant, we would consider putting a high rate bioroughing trickling filter upstream of our secondary clarifier. The reason we would do that is we want to remove any high levels of organic loading that could overwhelm the secondary clarifier, and that's why we would put a bioroughing filter in there. Again, it's a buffer or a shock absorber. We want to make sure that we level out our organic loading before it goes into a secondary process like a secondary clarifier. Okay. Some notes on filter performance, on how we configure and how we stage these. Okay. So for BOD efficiency, removal efficiency, we're looking at 80 to 85%. So the thing is, we've got to have an additional secondary treatment, because 80 to 85% of BOD removal, it's still not enough to meet your NPDES permit requirement. So we're still going to have downstream of this another secondary process to get rid of the remaining 15 to 20% of the BOD still left in the wastewater. But here's the thing. Recall our schematic. We're simply trickling wastewater over rock or over some type of filter media. We're not spending a lot of money or a lot of time treating that organic load. So this is a fairly low cost operational system. So if we eliminate 80 to 85% of our BOD, and we can eliminate aeration, for example, an aeration basin or an oxidation ditch, or really downsize those, that's money well spent when you think about it. By clipping off 80 to 85% of your organic load, and then you only got to treat 15 to 20%, whatever's left. Okay, so the efficiency calculation, we went over this last class, I believe. All we're doing is we're looking at the BOD strength coming in, which is what's leaving the primary clarifier. That's the primary effluent, but that's also what the influent coming into our trickling filter is. And so we're basically looking at in minus out divided by in times 100. You remember that little memory aid I gave you? In minus out, the BOD coming in minus the BOD leaving divided by the BOD coming in times 100. That's our percent efficiency. Okay. So we also try to, with staging, we try and arrange trickling filters in series, at minimum of 2, where the flow is going to pass through 2 filters. So think about it. We get rid of 80% of the BOD load on the first filter. So that's 20% left. And 80% of 20%, that's 16%. So we've just, by arranging the filters in a series configuration with 2 of them, we're now at 96% removal efficiency. Again, for a low cost system, that's just unreal. That's mind boggling when you think about the economics and you think about the efficiency. Okay. There are some limitations though. So for our modern NPDES permits, even if you do this a couple of times, you're still not going to get down to the levels that they want you to, that the regulators in their permit that they wrote want you to get down to. And that's understandable. But you are knocking a whole heck of a lot of the organic load out of the influent and effluent at a very low cost, a very efficient one. Okay. So how is this happening? So those bugs, those microorganisms, they're converting any dissolved compounds in the waste, like sugars, starches, fats, into physical solids. So they're taking that dissolved food for them, for these bugs, the fats, the carbs, the sugars, that's what's comprised of the BOD. They're metabolizing that and they're turning that into biomass. They're reproducing. Okay. And that those solids, those microbes, that slime, as it sloughs off, and even if it goes down to a secondary clarifier, it's now in a solid, heavier form, and that can settle out. So that's the interesting part. All we're doing here is we're just converting one source of organics, the sugars, the starches, uh, and fats, into the microbial mass or the slime layer, letting it fall off and then letting it settle out as a solid in another clarifier. Pretty slick when you think about it. We're letting natural processes uh, do a lot of this for us, and it's saving us a lot of money and time, and it's fairly efficient when you think about it. Okay, we can have for strategies and process controls. So, um, like I told you, these are natural processes. Those microbes, converting those organics, that high BOD content, converting it into biomass and then sloughing off. That's a natural process, but we do have some things we can do to help that along or control the process. We can have recirculation loops. And what that means is we can take that filter effluent or even secondary clarifier effluent, and we can recirculate it and send it to the head of the trickling filter again and have a second pass at that. So we can send that filtrate through the process a couple of times if we need to, and that'll really help with the efficiency as well. Okay. Uh, so here's something to think about, though. Pretty important concept. That recirculation rate, that's really, for a trickling filter, that's really the big and only way we can control the process. We can control the recirc rate. Okay, that's a heck of a test question for a level 3 or level 4 operator. Uh, what do we do? How do we control it? We can either decrease or increase that rate. And when you think about it, you're going to get a couple of different questions on your exam, maybe one or two on your exam, but it's well worth thinking about. For a trickling filter, the only variable you can control is the recirc rate. So you can increase it or decrease it. Think about what you're trying to do, and that'll give you the response you want: an increase in circulation rate for the trickling filter or a decrease. Think about that as you go through some of the homework problems and some of the exam problems. But that's about the only thing you can control in the trickling filter. For low flows, at nighttime, we get lower flows. Remember, we talked about this earlier on. We see a spike in incoming wastewater in the morning, a couple hours after people wake up and they shower, they cook, they get ready for work. So that's between 6 and 8 o'clock. Then a couple of hours later, all that wastewater flow starts hitting, the peak starts hitting the wastewater plant. Then it dies out. And then we see another peak, not as big, but we see another peak as people start getting off work and they go home, they cook dinner, they, wash clothes, they do whatever they have to do. And then like 7, 8 o'clock at night, we see a second peak because it takes a couple hours for that wastewater to hit the plant. Well, in the middle of the night, most everybody's in bed. And that's when you're going to see low flows coming into the plant. So the idea here is during the night, we're going to increase that recirculation rate to make sure that that distributor arm keeps turning around. Remember, I told you that distributor arm, the force or the energy that moves that arm around is that trickle that comes down, that spray or trickle. That's what's causing that arm to move. Well, if the flow is so low it can't cause that arm to move, we're just going to have a little trickle over one part of the filter. We want this wastewater applied uniformly throughout the filter media. So we're going to increase that recirc rate at night so that we have enough energy in that trickle to move that distributor arm around. Okay, so that would be another good test question. How do you handle this at night? What would you do to troubleshoot? Okay, dissolved oxygen. So we can also create an aeration process in that stream to make sure that we keep a dissolved oxygen level in our uh, wastewater at 1.5 to 2 milligrams per liter. That's where we want to operate this. And how can we do that? We can adjust the recirc rate so that that's what we're hitting on our effluent, okay, on our filtrate coming out. We can take a grab sample, take a look with our DO meter and say, okay, well, it's at 1.0 milligrams per liter. So we would slightly increase the recirc rate until we get up to 1.5 to 2.0. Okay, so that's another way that we can adjust to make sure we stay within this dissolved oxygen range. Another thing we have to look at is pH in cold weather. You remember we've talked about this. As temperatures get colder, the biological activity in our plant goes down. Okay, those microbes, they kind of get lulled into the winter hibernation. They really aren't hungry anymore. Okay, so we can also aerate, or our aeration is going to strip the carbon dioxide and raise the pH. Okay, so if our pH is falling below 7 and it's heading towards 6 or what have you, so it's more acidic, okay, we can aerate or increase our recirculation rate so that we're aerating that wastewater more. And by aerating it, we're going to get rid of the carbon dioxide. And I think we talked about this a little bit. When we have carbon dioxide dissolved in water, we have H2CO3, or carbonic acid, which is just literally dissolved CO2 in water. Well, that carbonic acid, or that dissolved CO2 in water, makes our water more acidic. It lowers the pH. So if we want to raise the pH, we aerate it, and that oxygen, as we increase the recirculation rate and that filtrate falls through the bottom of the under drain assembly, it's going to increase its dissolved oxygen level. It's going to kick out the dissolved CO2, and it's going to raise the pH to a range that we want. Okay. Also, during the winter, we're going to increase the recirculation rate, and by doing that, we're going to counter the slowdown in biological activity. Okay, so the recirc rate, although you look at it and you're like, oh my God, we can only control one thing in this trickling filter, correct. But depending on what you do, you can handle nighttime flows, you can handle dissolved oxygen levels, you can boost the levels of dissolved oxygens, you can handle cold weather conditions as well as lowered pH conditions. And it's just one of those things. It's one variable, but it can accomplish a whole heck of a lot if you use it correctly. Okay. Like I said, I find these trickling filters very interesting. I had a professor when I went to get my undergraduate degree in civil engineering. He absolutely flipped out in the wastewater course I had to take, that we all had to take as undergraduates. He just flipped out over trickling filters, and he must have spent 3.5 weeks on trickling filters. He loved them that much. And while I don't think they're the end all be all, I do think they're very valuable, and they are very interesting systems. Okay. Staging. We're going to show figure 7.2 in just a bit, but the idea is, as we talked about earlier, we can arrange trickling filters in series, and we can increase our removal efficiency of our BOD. And the idea here is we can have a primary, an intermediate, and secondary clarifier. We can recirculate the filtrate or the effluent in different patterns, so that we can manage any high strength flows coming in, any spikes in BOD coming in. We can also arrange them so that we come closer to meeting some pretty stringent effluent limits in our permit. Okay. So in this case, we have our influent coming in. We've got the heavy sludge and inorganics settling out in the primary clarifier. It hits the trickling filter, and that primary clarifier effluent becomes the influent for our trickling filter. The wastewater is trickled over that media, typically rock for a standard flow or plastic for a high flow, and we're going to have that slime layer, those microbes, metabolizing the BOD in this filter the effluent from the primary clarifier coming into our filter. They're going to metabolize it, and it's going to go down to the under drain assembly, and then we can recircuit and send it back to the head here, and we can have another pass here before it goes to the secondary clarifier, okay? And in the secondary clarifier, we are going to allow the microbes floating around in the effluent to metabolize that organic load as well, and then it heads out as effluent, okay? What we can also do is, again, a primary clarifier, the trickling filter, and the secondary, we can take a portion of that secondary effluent and we can route it to the head of the trickling filter, and then we can send it through the process a second pass. Okay, so there's two different ways of looking at a recirc pattern here for these trickling filters. Okay, and we talked about this. The previous slide was just a one stage recirc pattern. You can get pretty complex here though when you think about it. Here's your primary clarifier, here's your trickling filter, second trickling filter, and then your secondary clarifier. So what we can do is we've got influent coming to the primary clarifier, the heavier organics and inorganics settle out, send it to the secondary or to the trickling filter. We can also split it off and send it into another trickling filter. But take a look at the first trickling filter. We're recirculating it, and it's going to go through the primary clarifier again. Okay, so we've got this loop going on, and that's going to allow for a more efficient removal here by recirculating it here. And if there's any suspended solids here, they get another second pass at being settled out in the primary clarifier, and then we can split the flow. So we send this primary effluent into a second trickling filter, okay, and it can go to a secondary clarifier, and then we're recirculating that here, okay. So we're doing a couple of things. We're removing suspended solids by recirculating it through the primary clarifier, and then we're getting more of the dissolved organic removal by recirculating from the secondary clarifier to the trickling filter. And in this case, a little different setup. We actually have, from a primary clarifier, we've got a series flow through our trickling filters, goes to the secondary clarifier, and then a portion of that comes out and goes to the head of the first trickling filter. So in the first system, the first setup here, we're doing two things. We're reducing the suspended sediment load with this recirculation loop, and we're making our organic removal more efficient with the second circulating loop. In this case, we're probably satisfied with the suspended solids removal with the primary clarifier, but what we're doing here is we're focusing on that dissolved organic load. So we're trying to get as much out of that with this scheme as possible. And in this one, same kind of thing, a little simpler than the first configuration up here. So in this case, we are probably concerned with, but by virtue of the fact we're recirculating the outlet of the first trickling filter back to the primary clarifier, we're getting rid of some more suspended solids, and then we're passing it on along to the second trickling filter, and then we're getting rid of some more dissolved organic loading. Okay, so if I had to rate these, this one is probably the most efficient, probably acts as the biggest buffer, if you will, to that secondary clarifier, and handles both removal of suspended solids as well as removal of dissolved organic loading. This one, we're not really worried too much about the removal of the suspended solids. We're happy with that in the primary clarifier. This one is going to remove more of the dissolved organic load, and this one's the happy medium between the two. We are minimizing as much as we can reasonably the suspended sediment load, and then we're trying to also manage a high quality effluent with the dissolved biological load. So that's what I say when I say that we can have some pretty sophisticated recirculation patterns. It's just a matter of what you're looking to accomplish, and you can adjust this with respect to whatever influent you see coming into your plant. So like I said, these are pretty versatile systems. They're not the end all be all, but they do have their use. Okay. Level 3 and level 4 examinees, you should understand how to troubleshoot trickling filters. Okay. So you should understand what some of the problems you have are to begin with. You can have what's called media ponding. And what happens with media ponding, that slime layer that we talked about, it starts filling the voids between the rocks and it doesn't slough off. It doesn't fall off and fall down to maintain those voids. It's like you're clogging up your filter. You got a clogged nose or something. Nothing's going to pass through, or portions of the incoming influent off the primary clarifier, they're just going to pond up because those snot layers, that slime layer, is clogging up the voids. Okay, and that ponding, what that ponding can do, it's going to block that air circulation. You remember I told you earlier on, we want those voids present because it's going to allow airflow to go through and allow our microbes to get aerated and chomp away at those wastes. We want an aerobic or oxygen rich environment. Well, if we have ponding, we get the slime layer overgrowing and clogging up the voids, and we have ponding in the lower media, particularly, we're going to have an oxygen deficient or poorly oxygenated environment, and it's going to go septic on us. And you're going to have an odor problem. You're going to have low dissolved oxygen. Okay. In addition, we can have nuisance organisms build up. Snails and what are called Sakota flies or filter flies, they'll get inside the filter box, and then you're basically going to have to go in there and you're going to have to clean things out to get rid of them. That's what operational intervention is. You're going to have to clean stuff out and you're going to have a mess on your hands. Then you're going to have to start all over again building up that snot layer or that film on the media. And one of the short videos that I have in your YouTube videos shows you an example of red worms and snails inside an RBC, but it's the same concept here. Those are nuisance organisms. You do not want those to start popping up in a trickling filter. Well, how do you correct these? Remember the one variable we have in a trickling filter. I stress this again. The one variable we have in a trickling filter is the recirculation rate. So I told you when we have a trickle coming down off that distributor arm, we do not want it spraying down, because if we do that, we're going to strip away that snot layer, that biological film. Well, in this case, we've got too much of a biological film. So yes, increasing the recirc rate is going to have a higher pressure spray, and we are in certain areas going to want to clean up those voids or strip away that snot layer, that biological layer. So if we kick up the recirc rate, we're going to scour and clean off that biomass, and we can control the ponding, we can control the septic conditions, and we can also control the flies. We can get rid of them. Okay. Also, the ventilation rate in the underdrain, those channels that we talked about, we want to make sure those channels don't run at more than half full. And we do that because we want to make sure we have, from those air ventilation slots that I showed you in the first schematic, we want to make sure we got plenty of air coming in to keep everything aerobic. Okay, so that recirc rate, like I tell you, it seems like, well, I only got one tool at my disposal. You're absolutely right. But that one tool can handle a lot of things with the trickling filter, recirculation rate. The other rule of thumb that you should get out of this, or the one operating criteria or heuristic, is keep those under drain channels no more than half full or 50% full. Don't go above that. You go above that, you're probably going to cause yourself some problems. Okay. So you should know this. But again, the big variable here, adjust recirculation rate. You can increase it or decrease it. Think about what you're trying to do. That'll tell you whether you want to increase or decrease the recirc rate. Okay. A few other things you can do. Well, on maintenance, I'm sorry. So we're now going to switch from troubleshooting to maintenance. So you want to check that distributor arm. The orifices, you want to make sure that they're not clogged, that you're getting an even flow out of there. There's also some splash plates out of there. You want to make sure that those trailing ends of the splash plates are in good serviceable condition. The seal we talked about that allows that distributor arm to rotate around that column, you want to lubricate those bearings regularly and make sure that the seals are in good shape and your bearings are protected. Those stay rods that we took a look at, they're basically cables that hold up the distributor arm. Those are stay rods and turnbuckles. You want to make sure that those have enough tension to prevent the arm from sagging, because if it sags, you're going to have uneven distribution. You'll also eventually probably have a problem with your arm and your bearings. So those cables that looking parts there, the arm levels or the stay rods and turnbuckles, you want to make sure that they allow for that distributor arm to stay level. Okay. You want to make sure the holes in your distributor arm and on your dump gates, there's no rags that get in there. If there's any accumulated solids, you want to flush those out. And this is one of the areas, you remember I told you the preliminary treatment or pre-treatment, one of the reasons we want to get rid of rags is they'll cause all sorts of problems downstream. Here's one of the places rags can cause a problem. If a rag or some rags get into the distributor arm, it's going to clog up the holes. You're not going to be able to flush. So rags, like I said, something you want to treat and get rid of earlier on in the process. In the preliminary treatment process with the bar screens, with the communators, what have you, simply because this is one of the areas it'll cause problems. And whenever you're working on these systems, second time in the course, I'm going to mention to you safety protocols, particularly lockout tagouts for mechanical use units. Whenever you're working on these, you want to do a lockout tagout. You want to divert any influent. You want to isolate the system while folks are working on it and doing maintenance on it. Okay, another safety issue. Okay. So we talked about trickling filters, again, fascinating fixed media system. The second fixed media system you're going to see on your exams, and you should know something about, are rotating biological contactors, or RBCs. Now let's talk about some of the basics, okay? So what these are some big drums, if you will, and inside those drums, they've got these plastic, they're called corrugated, which means they've got kind of sharp surfaces, as we'll see a little bit. You've got these discs, and they're attached to a horizontal shaft, and about 40% of that barrel looking apparatus, 40% of it at any one time is submerged in a tank. It's just like a race tank, a racetrack tank. And you've got these big barrels that are just slowly moving under the water. They come up, they go above the water, under the water. And the idea here is when those discs rotate out of the wastewater, they're going to pick up liquid. They're going to have some of that wastewater. And as they rotate around, that wastewater is going to fall down. And that's how they're aerating it. That air, you're allowing that wastewater to pass down through the air, and you have aeration. That's what's happening here, okay? These are fairly slow moving drums. Uh, and remember, the drums, they're providing aeration. They're also providing uh, the method for that film growing on the corrugated plastic discs to dip down below the wastewater and take a chomp of food before they come up for air, and they metabolize that. They're very slow moving. They're going to have about one rotation per minute or one revolution per minute. So they're very slow moving discs or barrels, okay? That are powered or moved around by a sprocket and chain drive. Or you can also use, I've seen some places use air driven diffusers in between the discs that allow the movement of those barrels, okay? The minimum water velocity for this process, about a foot per second. You don't want to go above a foot per second. Remember, the magic number to keep solids in solution is 2 feet per second. that's in our collection system, and we want this to be less than that 2 feet per second, because if it's greater than 2 feet per second, we're going to strip that slime layer off of those corrugated plastic surfaces. So we're going to allow the suspension of biological material at 1 foot per second here. Okay, and this is what an RBC looks like, the cross section. Here's the corrugated media. Okay, it's just a big barrel, and what's going to happen is we're going to rotate that big barrel, and we've got these passages that are going to allow the wastewater to come down. And so as we rotate the barrel, we've got air where we've got 40% of the drum below the wastewater. It's going to come down through here. The microbes are going to suck up as much food as they can get. We've got wastewater in these systems, and then what's going to happen is, as it comes above the surface of this channel here, the wastewater is going to start falling down. Okay, as the wastewater starts falling down, it's going to come in contact with the air, and it's going to aerate the wastewater, so we have a nice aerobic environment here, free of odors. And the film that we talked about, that snot layer or biological layer, that's on the corrugated plastic surfaces here, and it's moving at such a slow rate that that film is still going to be attached as it rotates very slowly, 1 to 1.5 revolutions per minute, rotations per minute, and it's going to come down and do it all again. So that's all it is. It's just a low-tech way of having that fixed media, which is forming on these plastic discs. That fixed film gets dipped down in the wastewater, picks up the food source, comes up. Any wastewater that's still in the RBC falls down, aerates, and then the oxygen's provided to that film so that they can metabolize that waste. So, and again, this can be driven with a chain motor, chain sprocket kind of assembly, or it can have air diffusers that'll also diffuse and move it around, diffuse the wastewater with dissolved oxygen and move the contactor around. Okay. This is what the cross section of that plastic corrugated surface that I told you about, that's what it looks like. And, just like a honeycomb almost kind of pattern. And that allows that biological layer to form on these surfaces here. See, what we're trying to do is increase the surface area. Same thing as a trickling filter, but rather than trickling wastewater over the fixed media, we're moving the fixed media through the wastewater. That's it. We're moving the fixed media through the wastewater. Pretty simplistic, but very effective as well. Okay. And this is what one would look like. Okay. This is an RBC in action. Okay. That looks like that's portable. Obviously, it's not down below the wastewater surface. Okay. And here's where we would basically stage them. We could have, so here's the preliminary treatment, the bar screens, the grit chamber, what have you. Then we have the heavier stuff settling out in the primary clarifier. We get the effluent coming off the primary clarifier, and we have these tanks here in series, and we've got 4 RBCs, and they just rotate and rotate, and the wastewater gets moved through here, and those bugs or microbes on the film of those plastic surfaces, that's what's helping metabolize these wastes as well. And then what's happening here is the effluent coming off the RBCs, those reactors, they go to the secondary clarifier. Okay, we can even recirc this just as we did with the trickling filters. We can recirc this and send it back to the primary clarifier. We could even recirc it from the secondary up to the head of the RBC reactor, just depending on what we're trying to do. Okay, pretty slick when you think about it. And another view of this, you got an air control valve, you got a bearing, and some air diffusers. And this is as I mentioned earlier, those air diffusers, that air that bubbles up will also slowly move and allow these drums to rotate. Okay, so just a different way of moving the drum or the RBC and allowing air also, or to come in, and dissolved oxygen to come in, so it's an aerobic process. Okay. So here's the thing, a couple of very important points when we operate these. There's this thing called the continuous rotation law for an RBC. So we've got these drums or barrels suspended with a center shaft and some bearings. Okay. We don't want those things standing still too long. If we do that, those bearings are going to fail. We're going to create a problem for ourselves. So we don't want to isolate or leave these, stationary for too long. Okay. And here's another one, pretty big one. If we have a power failure, uh, every 4 hours, you want an operator to go in there and turn that barrel a quarter turn every 4 hours. Okay. You want to do that to make sure that one, the structural integrity is okay. We're not going to have those bearings fail. That weight is not going to cause bearing or structural problems. It's also going to allow uh, that biological film to just move along and be aerated as well as stay wet and get a chunk of food. Okay. So these are two big items here. You want to make sure these things don't stay stationary too long. And then in the event of a power failure for an RBC, you want an operator every 4 hours to make a quarter turn of that barrel. Two pretty big things. Another thing, uh, one of the reasons we want to make that turn is if we leave that portion of the barrel submerged, that film's going to keep growing, and we're going to have an unbalanced load, just like you do with your washer. You'll hear a rumbling if the load's unbalanced. Same thing here. If it means basically we've got too much weight on one side of the RBC, and we're really going to cause ourselves bearing problems and load problems. But that submerged biomass is going to grow, and the top, because it's not getting any food and it's drying out, it's going to die and slough off. It's going to fall off. So we're really going to have an unbalanced load here. And that's one of the reasons that we're going to want to, in the event of a power failure, have a real slow movement every 4 hours, a quarter turn of that, to prevent the unbalanced load. And if we try and start an unbalanced RBC, if it's lopsided in weight, we're going to damage the drive unit. So this is why this little operation here, in the event of a power failure, turning that RBC a quarter turn every 4 hours, that's why it's so important. It'll prevent the unbalanced load. And if we create an unbalanced load, we're going to destroy the drive, and our RBC is going to be out of commission for a while. Another thing to look out for is grit accumulation. So if we have a sludge or grit buildup beneath the discs, we're going to stop the rotation, and we're going to allow for septic conditions. We're going to not have the aeration we need. That grit and that sludge can block that. We're going to have septic conditions. We're going to have an odor problem, and we're not going to have an efficient removal of BOD. Okay. A couple of really good test questions for troubleshooting for level 3 and 4 on this slide. Okay. So we can also have multi-stage RBCs that we saw about earlier, and we've got some other indicators we can look at. So we can have what's called a plug flow design, and what that is, we can have baffles. So those baffles, they'll channel the outflow of one RBC into the inflow of another RBC, and we're going to have a differing growth profile, you can imagine, because the first RBC the wastewater comes in contact with, high organic content, high BOD, but let's say we have a series of 4. The last RBC is not going to see the same organic loading as the first 1 or 2 RBCs. So something to think about. Our growth profiles, as it's called, is going to vary between stages. Here's another good test question. A first stage indicator. Okay. We're dealing, as I mentioned, with heavy organic loads at the first stage of a multi-stage RBC setup. So if they're in series, and let's say we have 4 of them, RBC 1 at the beginning, 2 and 3 in the middle, and then RBC 4 at the end, the first stage is going to have a heavy organic load, and that biomass, it's going to look like a thick gray shaggy carpet almost, with low dissolved oxygen, about a milligram per liter. Okay, so that's how you know you got a first stage, and that's how it's going to start looking, is just a gray shaggy mass and low dissolved oxygen. Okay, um, also we can use this multi-stage setup to treat nutrients. And for nitrates, for example, or ammonia coming in, heavy nitrogen or heavy ammonium content coming in, um, when that organic BOD is depleted, the dissolved oxygen levels are going to rise to about 4 or 5 milligrams per liter at the later stages of RBCs in series, and it's going to act as a conduit or as a catalyst for these nitrifying bacteria to eat those nutrients, to metabolize those nutrients. Okay. And the nitrifying biomass compared to the first stage is a gray shaggy biomass. The nitrifying biomass, which is in like stage 4 of the RBCs, it's a thinner dark brown layer. Okay. Those are two good test questions. What does a first stage of an RBC look like? What does the biomass look like? It's a gray, shaggy biomass with low dissolved oxygen. Okay, so what does the fourth stage of an RBC in series look like? Well, for nitrification, it's basically nitrifying biomass. It's a thin brownish biomass, thin brownish biological layer. Okay, two good test questions there. Okay, if we can have an upset here, so if we have a huge amount of BOD coming in, the biomass can turn black, and we'll get like a toxic type chemical to the microbes, and it'll get an upset, and we'll get a milky white appearance in our wastewater there. So looks milky white, it's a toxic chemical upset, and that's if you're getting too much BOD coming in off of the primary clarifier. Okay, you're basically shocking the system at this point. So there's some good test questions here for troubleshooting. The level 3 and 4 folks, you may see these, but likely you're going to see stuff like, what do you do in the event of a power failure? Well, you rotate the RBC 1/4 turn every 4 hours, but you can never tell. So you do want to read this over, and the wastewater enthusiast video that I put on the YouTube video list, the very last one, it's about 20 minutes long, but I give that gentleman credit. He put together an outstanding video for this topic and what you can possibly see on a wastewater certification exam. That's 20 minutes of your time well spent. Okay. So if you have any questions, by all means, please post them on Canvas. I'm putting a discussion thread for each module on Canvas. Please ask questions. Happy to answer them. There's a weekly feedback quiz. Please give me feedback. If you don't like the way things are going, say so. If you want to see something different, if you want to review a concept, or if you learn something new, please let me know. That's your way to give me really immediate feedback. Homework assignment. It's actually a 19 question quiz as your homework. Unlimited attempts. Please take them. There's a few questions in there you are going to see on your certification exams. Please do take a look, okay? And remember, I told you this is a secondary biological treatment process. So this is definitely important for your level 3 and level 4 operators, okay? You do want to know this, particularly the troubleshooting. A reminder, this is what you're looking at for each exam level. Level 1 certification exam, it's general knowledge, safety, and routine maintenance tasks. Level 2, you want to know something about biological cycles, and you want to do some simple operational math, velocities, flow rates, that kind of stuff. Level 3, lots of math, lots of process control expertise and troubleshooting. Activated sludge, the next chapter that we go over, the next module, that's your bread and butter to pass level 3. Level 4, you're looking at advanced or material like nutrient removal, You want to know your regs inside out. You want to know management tasks like how to put together a budget. Okay, so this concludes the lecture for this module. I'm available via cell phone. We can arrange for a Teams meeting. I'm going to be back next week. So you got one more lecture on PowerPoint like this. And I hope you're getting something out of the class. I hope you're reviewing. Please be consistent in doing the homework. You don't want to wait till the last minute and do it all at once, okay? So I've talked with Pete. I'm going to see what I can do to export for the Lanel employees, to export the quizzes and the sample exams. You're going to start getting sample exams, full 120 question exams after the July 4th weekend. I'm going to spend July 3rd putting those together for you. I do want you to take those. Your grade is not dependent upon the grades you're getting on the homework or the sample exams. It is critical you do those. It's critical you take them. And I want you to do well on them because you're going to see that material on your certification exams. But I'm more interested that you guys are practicing right now, that you're picking up the material. If you view every lecture, if you do every homework assignment, you make an honest effort on them, you do the feedback quizzes, you take the certification exams, don't worry about the grade in the course. The grade in the course to me is minimal, but if you do all that, you're going to get a good grade. What I'm more interested in you doing is passing your certification exams. That's why it's critical you do the homework. Do it 3 or 4 times. Take the certification exams. Take them 3 or 4 times. Okay? The idea is to get practice in the computer quiz environment. The idea is to get familiar with the material. Okay? You do that, you're going to have a really good shot at passing your certification exams. If you got any questions, please email me. Contact me. I will be back in the United States next week, and we will pick up regular lectures at that point. I hope you guys are having a great day, and I hope everything is going well. Please contact me if you need anything, though. Please do.